We have now gone through A, and from A we now know that the total capital can be described using a Kremer-Lundberg process, since the total claim size could be modeled as a compound Poisson process, where the claim arrival rate was just the sum of claim arrival rates in the two lines of business, and where the claim size in this compound Poisson process is just a claim size that follows a mixture distribution, which is the average of the distributions of the claims in the two lines of business. Now, what we want to do in 2b, what we are asked to do in 2b, so in B, we are asked to find an asymptotic expression, for the probability of ruin as the initial capital tends towards infinity. Now, there are a number of different equalities that inequalities that can help us with this, or different approximation results that can help us with this. Mainly, I think there are three main results that can be useful related to the Kremer-Lundberg process that are pretty good to just recall. One, you have the Lundberg inequality. And two, you have the Kremer-Lundberg approximation, which kind of just fleshes out the Lundberg inequality a bit. And three, you have the ladder height version of the ruin probability approximation, which I just like to call Theorem 215. Now, we use these in different cases. The first two make sense to use if the adjustment coefficient is well defined. And typically, since the adjustment coefficient satisfies an equation where the moment generating function of the claim size occurs, typically we use the first two here for light-tailed claims. And third one here, it was derived especially for usage together with heavy-tailed claims. So I'll just write here for heavy-tailed claims. And what I actually mean by that is for claims that follow a sub-exponential distribution. Now, what do we have in our case? Well, we want to find an asymptotic expression for the ruin probability. So the question is, should we use the Kremer-Lundberg approximation from the light-tailed case, or should we use the ruin probability approximation from the sub-exponential case? Well, we have two lines of business, right? And we have written up a Kremer-Lundberg process in this form, where the claim size follows a mixture distribution. Now let's try to see what happens to this tail probability when x becomes large. So for large x, well, this tail probability will be dominated by what? Well, it would actually be dominated by the second term. So it will be dominated by the Pareto term. Can you see that I've written term here? As such. By the Pareto term, namely 1/2 multiplied by 3 divided by 3 plus x to the fourth. Because as long as we just go sufficiently far out in the tail, this decay will be much more intense than this decay. So the Pareto part of this mixture distribution decays very slowly compared to the exponential part. And therefore, the heavy-tailed line of business plays a larger role when considering ruin probability. In fact, I can even make this a bit more precise in the sense that if we consider what happens when I take the probability of yi being greater than x and divide by the Pareto tail, then of course the second term just becomes a +1, while the first term gives e to the minus x divided by 3 divided by 3 plus x to the fourth. And if you let x tend to infinity, then because the exponential part goes to 0 much quicker than this polynomial part, then this entire thing will tend towards 1 as x tends to infinity. So, in fact, we actually have that the tail probability is asymptotically equivalent to the Pareto part of the mixture's tail probability. So when we have to consider, are we going to use the Kremer-Lundberg approximation or the ladder height version, then it is quite apparent that what we're going to use here is theorem 215, since our claim sizes exhibit sub-exponential behavior. Okay, so now let us apply 215. So by 215, we have that the ruin probability is asymptotically equivalent to a fraction where on the top we have the claim arrival rate, which in our case is 1/2. So if you're not sure about what I'm putting inside the formula and what the formula is, just take your Schmidtly notes and find theorem 215. So you have the claim arrival rate divided by the premium rate, which in our case is 1, and then you have to subtract the expected number of claims, which in our case is the claim arrival rate multiplied by the expected claim size, and our expected claim size, well, is equal to 1/2 multiplied by the expectation of y1 plus 1/2 multiplied by the expectation of z1. And then we have to multiply by the integral from 0 to infinity of the tail of our claim size. Okay, so we're going to write up what this is. You have 1/2 divided by 1 minus 1/2, and then we have 1/2 multiplied by the mean value inside an exponential distribution with parameter 1, so that's just 1, plus 1/2 multiplied by the mean value for a Pareto distribution with parameters 4 and 3, and that mean value is 3 divided by 4 minus 1. You can either calculate this by hand or just find it on Wikipedia. That's up to you. And have this, and we're going to take the integral of the tail probability of the claim size. And since the claim size is asymptotically equivalent to this Pareto part, what we can just do is, as long as U is sufficiently large, then it suffices to integrate over the Pareto part of the integral, since the other part will just tend to 0, right? So for U sufficiently large, it suffices to just consider the Pareto part. This is then equal to 1/2 divided by, so here we just have 1/2 and here we just have 1/2, and what you then have is, I guess, 1 minus 1/2, and that gives us 1/2 as such. And let's also just calculate this integral here. We take the 1/2 inside the integral outside, and there's also a 3 to the 4th that we can take outside. And inside here, what we've got left is just the integral from U to infinity of 1 over 3 plus x. And when we calculate the antiderivative of 1 over 3 plus x, what we get is 1 divided by 3 multiplied by 1 divided by, we have 1 divided by 3 plus x to the 4th, yeah. So the antiderivative of that is 1 divided by 3 multiplied by 1 divided by 3 plus x to the 3rd. And I think we should also have a minus here, right? Because when I then differentiate this, I get a 3 here. This becomes a to the 4th, and there's also a minus because it's actually the exponent is minus 3rd. So this is right. Okay, so we then take the limits from U to infinity, and this then gives us 3 to the 3rd divided by 2 multiplied by 1 over 3 plus U to the 3rd, since the negative term where we plug infinity into x's place just yields a 0. Now, for U tending to infinity, whether we add a 3 to U or not actually doesn't really matter. So this is asymptotically equivalent to 27/2 multiplied by 1 over U to the 3rd. And this is a result that holds as U tends to infinity. So we have now found an expression which gives us the ruin probability for large values of u. And we can see that in this case, our ruin probability has polynomial decay, has cubic decay, actually. So ruin probability has cubic decay, which isn't as nice as exponential decay, which we can get in the light-tailed case, but we'll take it. So that was the solution of B.